In this video, we will be describing the types of nuclear particles that can be used or emitted during natural radioactive decay processes, and then describing the main types of those nuclear decay reactions. It is very important that you be able to recognize not only the name, but also the symbol, the isotope symbol or notation for each nuclear particle type. The first one we discuss is the alpha particle. This is the one that's given off by very heavy isotopes. This is the fastest way for those heavy isotopes to start to lose some mass. If the alpha particle sounds familiar, it should. If you remember your history lesson in first semester chemistry, Rutherford's experiment used alpha particles. And so an alpha particle is technically a helium ion. It is sometimes referred to or used as the alpha notation. So that's the Greek letter alpha we're using there. The second one is the beta particle. And a beta particle is simply an electron. And there is a notation missing here. So remember, electrons are negatively charged. So that would be a -1 for your atomic number. And of course, we say electrons have no mass. Or we can use the Greek letter beta for this. So we use those interchangeably. A positron is simply a positively charged electron. And this has to do with the antimatter substances that we don't get into, but really a positron is the antimatter particle of an electron. A proton, hopefully this sounds really familiar. Remember when we were in our acid-base chapter, we were discussing the proton as the hydrogen ion. So notice that in these notations, we don't use charges. So this is technically an ion, as is the helium ion up in our alpha particle. But because the exchange of electrons is so much less energy than the exchange of the nuclear reaction, we dismiss the discussion of ions here. So our proton notation, we would have a proton or an atomic number of 1, therefore a mass number of 1, right? No neutrons in here. Or we simply use the letter P to represent our proton. A neutron is represented by a 0 for the atomic number and a mass number of 1 to represent the 1 neutron in there. And a gamma ray. This is included in our list of particles, even though a gamma ray is not a particle. If you remember from first semester general chemistry, you heard about gamma rays, or you might have noticed gamma rays when we would discuss the electromagnetic radiation spectrum. So gamma ray is a very high energy type of electromagnetic radiation. When we talk about nuclear chemistry, one of the concerns that, of course, everybody has is what happens with exposure. And it turns out that the larger the particle, the less damaging it is, right? The larger it is, the less it can penetrate through. So here's a wonderful diagram showing that alpha particles are actually stopped by a piece of paper. They're so large that anything stops them. So we don't hear about damaging effects of alpha radiation. Beta particles are simply electrons, considerably smaller. You've heard of beta particles. You might not have known it. Maybe you're familiar with it if you work in a medical field, but beta particles are simply X-rays. When you get an X-ray, it is a stream of electrons coming through to generate the image. So, of course, when you go to the dentist office, the first thing they do before you get your X-rays is to lay that heavy lead shield on your chest so that you are minimizing how much exposure you get to the beta particles. So notice it can penetrate through your body, and it is stopped by a thin sheet of metal. A neutron is even smaller. It can penetrate through metal. It takes water to be able to stop neutrons. Gamma rays, these are very damaging. Again, they're not a particle, it's just a type of radiation. And so it can actually even penetrate through concrete. So it takes a thick sheet of lead to stop gamma rays. If you've heard the stories about people building bomb shelters back when atomic bombs were a threat, they were lining those shelters with lead. And that was so that if a bomb happened to go off in the near vicinity, the lining of the lead on the outside of the shelter would stop any gamma radiation from penetrating. The types of nuclear reactions that we are going to discuss, we're going to focus on the radioactive decay or emission reactions. These are natural processes that our unstable nuclides are going to undergo, and usually in multiple steps until they become a stable isotope. General notation that we're going to use with all of our reactions, the reactant is always referred to as the parent nuclide. The product of that is the daughter nuclide. And then there's the radiation or the radioactive particle that's given off. One key thing to recognize when we use the words decay or emission, we always mean that that radioactive particle, the list we just went through, those are always on the product side. So again, decay or emission means that that radioactive substance or that nuclear particle is going to be a product. The next type of nuclear reaction, you've likely heard of this, is fission. This is when we bombard a heavier isotope with a neutron to break it down into lighter isotopes. This is actually the process that occurs in nuclear reactors. The next type is fusion. So fusion is the exact opposite of fission. Fusion is where we combine two lighter isotopes together to form heavier isotopes. In the universe, the only natural process, or the highest natural process of fusion, can produce iron. Transmutation is the last one, and we'll talk about examples of this. This is where atoms are bombarded by high energy particles to create new elements or isotopes. So these reactions happen in particle accelerators, either linear or circular. And again, isotopes are being bombarded by high energy particles so that we can create new substances. And again, we'll see examples of that. In our next video, we're going to go through examples of the types of natural decay and emission processes that happen for nuclides, radioactive nuclides. And our goal in those is to predict either the parent nuclide, so remember the reactant is the parent. More commonly, our goal is to predict the daughter. But as long as we only have one unknown in an equation, we can predict anything. Because we're changing elements in these nuclear reactions, we can't balance equations by balancing atoms anymore. What we balance now are the atomic numbers and mass numbers. So the numbers of protons and neutrons have to be the same on both sides of an equation. And so we do that by adding up all of those. So notice in our parent nuclide, we have a total of 84 protons. That means on our product side, we have to have a total of 84 protons. And that comes from the sum of 82 from lead and 2 from our alpha particle. And then the same thing happens in our mass number. Since our parent nuclide has a mass number of 212, we have to have a total of 212 on the product side. 4 of those come from our alpha particle, and so that means the remaining 208 come from our lead isotope. And so by doing this math, addition and subtraction, we can actually identify, as I said, commonly the daughter nuclide, but it is possible to also identify the parent nuclide in a reaction. And so again, in our next video, we will discuss how we determine the products of these decay processes.